first example. In our first example, they give us the graph of f of x. They don't tell us the equation, although looking at it, you might recognize it as one of the ones you've memorized. Sketch the graph of y equals negative 1/4 f of x. So this is in function notation. And after we've done it in function notation, I'll show you what the same question would look like in regular notation or explicit notation. So we have our original graph, f of x, and we're asked to graph negative 1/4 f of x. So we notice that the negative is outside of the function, the 1/4 is outside of the function. And so everything here is going to affect the y coordinates. Another thing that we're going to start to do more of is go to our original graph and label some key points and look specifically at those key points. Obviously in this graph, that's the most important point, 0, 0. Now when we think about what's going to happen with that negative 1/4, we're going to describe it first. The negative is a vertical reflection. And the 1/4, will that compress it vertically or stretch it vertically? Now everything outside of the function that affects your y values, everything outside of your function that affects your y values is going to sort of be how your gut feels it should be. You see a 1/4, you want to multiply by 1/4. Perfect. And because we're multiplying by a fraction, that's going to compress it. So first I describe in words what I see. Vertical reflection and vertical compression. You will get some questions that say that. Describe in words what transformations are needed to graph y equals negative 1/4 f of x. The next thing I'm going to do is write down what we're going to do sort of algebraically. If I need a vertical reflection, that will multiply the y value by a negative 1. And if I need a vertical compression, which will multiply the y coordinates by 1/4, I can put both of those ideas together and say we're going to multiply all of our y coordinates by negative 1/4. And the way that we're going to get our specific points to graph this function is, well, we've chosen 0, 0 already, but we're also going to choose one point on the right side of 0, 0 and one point on the left side of 0, 0. Now the question in this case becomes, well, which point should I choose? A, it doesn't really matter because all points will work, but B, there might be some points that work nicer than others. If I have to multiply my y values by negative 1/4, which point is that easier to work with? 1, 1 or 4, 4? 4, 4. So if I choose on this side 4, 4, that will be a nice point to use. What are some other nice points I could use? I could use negative 4, negative 4, 4 on this side, or I could choose negative 8, 8. That also will work out nicely, right? Because those are numbers where the y coordinate divides nicely by 4. So that would be why I'd choose those. So if I chose those 3 points, and it would not have been wrong to choose negative 4, 4 on the other side. And then I'm going to put an arrow on each of these points to say, how is it going to get changed? And above the arrow, I'm going to describe what I'm going to do. So we know that we have a vertical reflection and a vertical compression. I'm going to add a few more words to this. With the vertical compression, to be more descriptive, we can write by a factor of 1/4. So whenever we have a stretch or compression, we can say what it is by writing by a factor of. And now if I multiply all of my y coordinates by -1/4, well, this will stay 0, 0. This becomes 4, -1. And this point becomes -8, -2. The other thing that this unit has the potential, well, I almost guarantee that this is going to happen to you, is you're going to make a mental math error somewhere. We're going to do lots of mental math, adding, subtracting, and multiplying, right? And so it's going to be very easy for you to see this 8 and say I'm multiplying by -1/4 and accidentally forget the negative. That's going to happen. Sometimes you're going to be multiplying. Now these ones, the coordinates are the same, right? And that is 4 and 4, 8 and 8. But sometimes you'll have a point that's 2, 8. And you're right, I want to multiply my y by 2, and you multiply your x by 2. Can you see yourself accidentally doing that sometime? It's very easy to do. So how do we guard against that? Because now I've got my 3 points. I'm going to plot those 3 points. I'm going to be extra careful in this example in particular because when I go to 4, -1, this is what I would be very tempted to do. Go to 4, go down 1, and mark it. What's wrong with that? The scale is going by 2s. Another thing, can you see yourself just all of a sudden counting a box and saying, I'll go down by 1 and mark it? But the scale here is going by 2, so that little green dot should really be right there. And when I go to mark -8, -2, well, since the scale is going by 2, that would be right there. Connect your dots and draw your graph. So how do we safeguard against making a crazy mistake? Well, after doing and getting your points, plotting and drawing them, you're going to check, does the shape match up with the shape that I started with, and does the shape follow my description? So my description says I need a vertical reflection. Can you see that would take that red graph, flip it down, and now it's pointing down? Our graph is pointing down, so that makes me feel pretty good. And then we need a vertical compression. A vertical compression takes above and below the x-axis and squishes it towards the x-axis. Now, after this red graph gets flipped down, it's completely below, but can you see that it got really squished and is much wider than it was before? So by thinking through what is happening, you can get an idea what the graph should look like. And the points give us our specifics, because we're going to need to not only have the right shape, but have specific points that are correct. And one of the things that you're going to do and practice on your graphs is after you've labeled those points, you're going to go and actually label those coordinates. So I'm going to write 4, -1, and -8, -2. We'll check to make sure that we have arrowheads on the end of our graphs. And now finally it says state the domain and range of each function. So my original one is red. I'll do my domain and range in red, and my new one is green. I'll do my domain and range in green. And so the domain in my original one, again, we remember that with our textbook there would be arrowheads saying that it goes up forever and goes wider forever. In this case, that means our domain is everything. For the range of our red graph, the smallest value is 0, and it goes up forever. So this would be set notation in red. I'll also do set notation in green. The domain is still everything, but now my range is less than or equal to 0. That's the question, but I also want to look at this question using actual explicit equations. Explicit equations are when you don't have functions in there, you just have x. And this is a great example for that because you recognize that red graph. That was one of the graphs that we did at the beginning of the year. So we could write the equation of our red graph. Uh-oh.